Hello, welcome back once again. Today we're going to look into this Lambert W function. I've been solving equations in this form. Let's say we have x raised to the power of x is equal to a. We have a raised to the power of x plus bx is equal to c, and also a raised to the power of x is equal to b times x. So all these type of equations are solved using the Lambert W function, and I'll be doing that on this channel. But today we're going to look into this Lambert W function, that is introduction on this special function, and let us understand this function properly today. Okay, are you guys with me? So let's go. Okay, now just like we have the natural log of x, and we know very well that this is the inverse function of a function, right? And what is that function? The function is e raised to the power of x. You get the idea? Okay, but today we are looking into this Lambert W function. So let's say we have the Lambert W function is equal to the inverse function of a function. Then if you talk about this function, the function is going to be equal to x multiplied by e raised to the power of x. So you can see they are somehow related, right? Take a look. We have w of x, we have natural log of x. And here we have that the g of x is e to the power of x. And here the f of x is when the g of x is multiplied by x. So I think they look somehow similar, right? But this one is more powerful. Okay, now let's talk about the graph of this function x times e raised to the power of x. So the graph looks like this. So here, this is how the graph look like. I don't know if I'm getting it accurately, but this is just a rough plot of the graph of that is x times e raised to the power of x, right? And we know that x is greater than or equal to -1 from the graph, right? So we can talk about the domain. So we can say that the domain is what? -1 all the way to infinity, right? And when we talk about the range, we say that is when you put -1 into the function, so it will give us -1 times e raised to the power of -1, and this will result to -1 over e, right? So we have here -1 over e. When you put infinity, we get infinity, right? So this is the range and this is the domain. So if you talk about the domain and range of the w of x, remember the w of x is the inverse function of this, right? So the range of this function will be the domain of the Lambert W function. So we can say that the domain of the Lambert W function is the range of e times of x times e to the power of x. So that is -1 over e to infinity, right? Why the range will be the domain for this function, for the function itself, right? So that will be -1 to infinity, right? Okay, cool. So now we have the following properties for the Lambert W function. So let's say we have to evaluate the Lambert W function of f of x. So this is equal to the Lambert W function. You know the function itself, that is x times e raised to the power of x. So this is equal to x. So you see this is really helpful. Okay, so we always solve those equations I mentioned earlier, like x to the power of x is equal to a to the power of x plus b to the power b times x is equal to c, or a to the power of x is equal to b times x. So we always try to obtain something that will look similar to what is in this input, right? So that when you take the Lambert function, the left hand side or the right hand side, wherever this is, it will simplify nicely. Are you guys with me? Okay, cool. Now we have the second property here. And what's that? Let's say we have to take the f of the Lambert function. So let's see what this is going to result. So remember, f of x is x times e to the power of x. Therefore, this will be the w of x, right, multiplied by e raised to the power of the w of x. So this here is also equal to x. Wow, interesting. So if you divide both sides by the w of x, you will find out that e raised to the power of the w of x is equal to x over the w of x. So you can see these nice properties, okay? So we have this one here, which we generate this one from this one, right? Okay. Now let's solve this equation. X raised to the power of x is equal to 5. Let's make the following observations first. So we know that 1 raised to the power of 1 is equal to 1. Remember, we have x raised to the power of the same quantity x. So if we have 1 as the base, we also have 1 at the exponent, okay? So you get it? Okay, now we have here 2 raised to the power of 2 is equal to 4, right? We have 3 raised to the power of 3 is equal to 9. So you can see that this one here is less than 5, while this one is greater than 5. So this is telling us that our solution lies between 2 and 3. So we can say 2 is less than x and x is less than 3. Okay. Now let's talk about how we can solve this equation using this Lambert function. So we have the natural log of x to the power of x, that is taking the natural log of both sides, is equal to the natural log of 5. Okay, so with the property of logarithm, we know that log of a to the power of b is equal to b multiplied by the log of a. So this right over here will be x multiplied by the log of x. So this is equal to the natural log of 5. Okay, now here comes the trick. So we are going to rewrite this left hand side. Let it look similar to x times e raised to the power of x. So we need to obtain that at the left hand side. But look at this here, we have x here. And if you recall this property or this identity, that a can be written as e raised to the power of the ln of a. So if you rewrite this x here in this form, it will be e raised to the power of the ln of x. And here we have the ln of x. So this is equal to the ln of 5. Okay. So the left hand side is similar to this. X times e raised to the power of x. How? We can write it as the ln of x multiplied by e raised to the power of the ln of x. And from the right hand side, this is equal to the ln of 5. Now we can take the Lambert function on both sides. So you see when the Lambert function comes in, right? Okay, cool. Now take a look at the left hand side. Remember, from the definition, we know that the Lambert function of x times e raised to the power of x is equal to x. So you can see that the power of e is equal with this expression. So look at this, they are equal. And if we take a very look at this place, this and this, they are equal. So we take one of it out. So this is ln of x from the left hand side. So this is equal to the w of ln of 5. Okay. So now we take the common base of e. So you see that from here that x will be equal to e raised to the power of the w of ln of 5. So, well, actually, we have a property that we can use to write this. So let's check it out. Now look at this place. We see e to the power of the w of something is equal to that thing over the w of that thing, right? So here we have e to the power of the w of something, and that something here is the natural log of 5. So this will be equal to the natural log of 5 divided by the w of the natural log of 5. You see, then the question here is, how can we get the approximate value? So this is the exact value for x. Don't forget that. So the next question is, how can we get the approximate value? So you can use the Wolfram alpha for that. So you can use the Wolfram alpha, but if you want to impute this in the Wolfram alpha, we don't use W. The Lambert W function, do not forget, is being understood by the Wolfram alpha as the product logarithm. Okay, so we use the product, so it is also called the product logarithm or the product log. So for you to impute this in the Wolfram alpha, remember we have the ln of 5 divided by the W of ln of 5. So Wolfram alpha, we understand this in, if you write this as capital letter N, then small n of 5, then divided by, or you put your slash anyhow you want to write it. So the W here, you will write it as the product log. So that is how the Wolfram alpha, we understand what we are talking about. So put your bracket and put the capital letter N and the small n, then of 5. Okay, so when you do this, you will find out that X is approximately equal to 2.129 372 482 and 76. So this is the approximate value for X in the equation x to the power of X is equal to 5. So you can check it out. Thank you for watching. Please, if you really enjoyed the video, I did this because some of my fans have been asking me to make an introductory video on this particular function, the Lambert function, and I have done that today. Thank you for watching. Please do not forget to subscribe.